Okay, imagine this. You just dropped a needle on a hardwood floor. Right. Kind of annoying. But what if I told you that that could actually help you figure out pi?
Yeah, that's Buffon's needle problem. It's really cool how, um, you know, s- randomness can connect to some pretty fundamental math.
So we're talking about that famous number, pi, right? I am kind of skeptical, I gotta say.
Yeah.
Needles and pi, how are those two things even related?
Well, it all started in the 18th century with this French mathematician, Georges-Louis Leclerc, Comte de Buffon.
Wow.
He posed this question. What if you've got parallel lines, like, floorboards, and you drop a needle that's shorter than the distance between those lines?
Mm-hmm.
What are the chances that that needle's going to land crossing one of the lines?
Okay, so I think I understand the basic setup, but I'm still not seeing the pi connection. We're talking about needles and lines, not circles.
Well, the key is the needle's rotation,
Okay.
because the needle, when it falls, it doesn't just, fall in one position, right? It spins around
Yeah.
full 360 degrees. And that rotation brings in the idea of circles and angles, which is where pi comes in.
So the angle of the needle when it lands, that's like a crucial part of this whole thing.
That's exactly right. Buffon, what he figured out was that the probability of the needle crossing a line depends on a couple things. One is the ratio of the needle's length to the distance between the lines.
Okay.
But the other one, surprisingly, is pi.
You're telling me I can figure out pi just by dropping needles?
Yeah, it sounds kind of crazy, but there's actually this really cool interactive simulation you can check out. You can drop virtual needles, and it even lets you run it automatically for hundreds or thousands of drops.
Oh, wow.
Yeah, and it shows the needles that are crossing lines in red and the ones that aren't in blue.
Okay.
And as you keep dropping needles, you can actually watch the results converge toward pi.
That's amazing. So it's like we're using randomness, like random needle drops to figure out this really precise number.
Yeah, and it's a really great demonstration of how a chaotic process can actually lead to a specific mathematical value. Now, Buffon, what he did was groundbreaking. But another French mathematician, Laplace, he kind of took this and went a step further.
Okay.
And he said, well, what if, instead of just parallel lines, what if we use a whole grid of squares?
A whole grid. Okay. That sounds a lot more complicated to me. Like, how could that possibly work?
So it's still about needles and lines, but using a grid actually makes the whole process of figuring out pi more efficient.
Wait, more efficient? How does adding more lines make it easier?
So it comes down to this concept called negative correlation.
Yeah.
Basically, when the needle crosses a horizontal line on the grid, it's less likely to cross a vertical line, and vice versa.
Oh, okay. So they balance each other out.
Exactly. And that balancing act actually helps to reduce the variability, the randomness in the results. Think of it like you're trying to guess the average height of everyone in a room. You're going to get a much better guess if you measure a mixed group of people, not just the tallest ones or the shortest ones.
Right, right. It's all about getting a good sample, a good representation.
Exactly.
So with this grid and this negative correlation, are you saying we can get a more accurate estimate of pi even with fewer needle drops?
Exactly. It's
Great.
like the grid helps us to get a more balanced and representative sample. And this whole idea of negative correlation, it's not just limited to needles and grids. It pops up all over in statistics and computer simulations, and it can really make things a lot more efficient.
This is incredible. So Buffon's needle, it's not just some random math puzzle. It's actually connected to some pretty powerful techniques that people are still using today.
Yeah, it's a great example of how these simple ideas can have a really big impact.
Okay, I'm hooked. So tell me more about these Monte Carlo methods. What are they and how do they actually work in the real world?
Well, imagine you're trying to calculate the area of a really weirdly shaped lake. It's got all these curves and bends. Measuring that directly would be a nightmare.
Right.
But with a Monte Carlo method, you could just randomly scatter a bunch of points over the area and see how many of those points land inside the lake.
Okay.
You scale that up, and you get a pretty good estimate of the lake's area.
That's kind of like throwing darts at a map of the lake and seeing how many hit the water.
Yeah, exactly. And the more darts you throw, the better your estimate's going to be.
Yeah.
And the same idea you can apply to all kinds of things like predicting how the stock market's going to move, or simulating how molecules behave, or even creating those really realistic computer graphics you see in movies.
Wow, I never would have thought that dropping needles could be connected to all these different things.
It's really remarkable.
So Buffon's needle, it's more than just a curiosity. It's like the starting point for a whole bunch of really powerful techniques.
Absolutely. But before we get too far ahead of ourselves,
Yeah.
I think we should take a closer look at how the place's grid method actually makes calculating pi more efficient.
Yeah, that sounds like a great place to start part two of our deep dive into Buffon's needle problem.
Okay, so we got this grid,
Yeah.
right? And we've got our needle, we'll call it L for length.
Hmm.
And each square on the grid has a side of length t.
Got it.
And the needle's got to be shorter than the side of the square. That's important.
Okay, short needle, grid of squares. What are we even looking for when we drop the needle?
We're looking to see what the probability is that the needle's going to cross at least one of those grid lines.
Okay.
And it might sound a little weird, but the easier way to do that is actually to figure out the probability that it doesn't cross any lines.
Okay, so what are the chances that the needle just, like, lands completely inside one of the squares?
Right. So think about this. The needle, it lands somewhere in a square. It can be anywhere inside that square, and it can be pointing in any direction.
Right.
So some positions in rotations, they're going to make it cross a line, and some won't.
Right.
We want to focus on the safe zone, where it can land without touching any lines.
Okay, so we need to, like, define that safe zone. How do we figure out what that looks like?
Well, the size of that safe zone actually changes depending on the angle of the needle.
Okay.
So imagine the needle's almost parallel to the horizontal lines. It has a lot of room to move up and down without hitting a line, right?
Right.
But it's got very little room to move side to side before it bumps into a vertical line.
Yeah, if it tilts a little, it's going to hit a vertical line.
Exactly. Now imagine the opposite. The needle is almost vertical.
Okay.
Now it's got plenty of space to move left and right,
Mm-hmm.
but not a lot of space to move up or down.
I see. So the safe zone is, like, constantly changing as the needle rotates.
Yeah, that's the key. And so to figure out the probability, the overall probability, we got to think about all the possible angles the needle could land at.
Right.
And for each angle, we need to figure out how much safe space there is.
Okay.
Now, this gets into some calculus, but basically, you can calculate a volume representing all those safe positions and orientations.
Wait, volume. But we're talking about a needle on a flat grid, right?
Right. So it's kind of like, think of it as the volume of possibilities in 3 dimensions. So you get the needle's position along the x-axis, along the y-axis, and then you've got its angle of rotation.
So those three things define, like, all the different ways the needle could land.
Exactly. And so we're looking at the 3D representation of all the ways the needle can land without hitting a line.
Right, right.
And when you compare that safe volume to the total volume of all possible positions, that gives you the probability of the needle not crossing a line.
Okay. And so then to get the probability we're actually interested in, the needle crossing at least one line, we just subtract that from 1.
Exactly. And when you do all the math, here's the crazy part. Pi shows up in the formula. Even with this grid setup, you can still use this experiment to estimate pi.
Wow. But you said earlier that the grid is actually more efficient for estimating pi than just the parallel lines, right? Why is that?
It all comes back to that negative correlation.
Okay.
When the needle crosses a horizontal line, it's less likely to cross a vertical line and vice versa. That balancing act, it's really important.
Right. I get that they kind of counteract each other, but how does that actually make it more efficient?
So it helps to reduce the variability, the randomness in the results.
Okay.
Like I was saying before, if you're trying to get the average height of people in a room,
Mm-hmm.
you want to measure a mix of people, not just the tallest or the shortest, right?
Right.
So with the grid, that negative correlation helps us to get a more accurate estimate, even with fewer needle drops.
It's like the grid is giving us a more balanced sample.
Exactly. And like I said before, this whole idea of negative correlation, it's not just about needles and grids. It's a really useful tool in statistics, computer simulations, all sorts of stuff.
Wow. So this grid, it's not just more complicated, it's actually a more powerful way of getting to pi.
It really is. It shows how sometimes a little bit of complexity can actually make things more elegant.
Yeah.
Now, we've talked a lot about the theory behind this, but I'm curious, have you ever tried actually doing Buffon's needle at home? I mean,
Yeah.
could you actually estimate pi by dropping, like, toothpicks on a piece of paper with lines on it?
I think I might actually try it. It sounds kind of fun to do that at home.
Mm.
I'm not sure I have the patience to drop, like, thousands of needles, though.
Yeah, it would take a while if you want to get, like, a super accurate estimate of pi.
Yeah.
But even just doing, 100 drops or so,
Yeah.
that could give you a good idea of how it works.
So what would I need? Just, like, needles and some paper with lines on it.
Yeah, pretty much. You can draw lines on the paper. You could do parallel lines. You
Yeah.
can do a grid, if you want to try the Laplace extension.
Mhm.
And you can use needles. You could use toothpicks. You could use anything that's like straight and shorter than the spacing between your lines.
Okay.
You just drop them randomly and keep track of how many cross the line.
And then after enough drops, the magic of Buffon's formula starts to show itself.
Exactly. And it's cool to see how these random events, each individual needle drop,
Yeah.
it eventually adds up to this specific values, kind of like, flipping a coin.
Right.
If you flip it a couple times, you might get all heads or all tails,
Mm-hmm.
but you flip it 1,000 times,
Yeah.
you're going to get pretty close to 50-50.
So even in that randomness, there's like this underlying order, a pattern that's there.
Yeah, exactly. And Buffon's needle, it's a really good example of that.
This whole deep dive has been really fascinating. We went from like dropping needles on the floor to all these like powerful techniques that people are using all over the place.
Oh, yeah.
I never would have imagined.
It just shows the power of curiosity, right? Like looking at everyday things and asking these kind of weird questions.
Yeah.
Sometimes the most interesting stuff, it's hiding in plain sight.
Makes you wonder what other things are out there just waiting to be discovered.
Yeah, who knows? Like maybe there's a mathematical breakthrough hiding in the way the coffee stains dry or, the patterns of leaves falling off a tree.
I like that. So to all our listeners out there, keep your eyes open and stay curious because you never know where you're going to find the next big math adventure.
Exactly. And in the meantime, if you want a fun way to explore the world of math, I highly recommend giving Buffon's needle a try.
Yeah, you might be surprised what you can learn from just a few drop needles and a little bit of patience. Well, thank you so much for joining us on this fascinating deep dive into Buffon's needle problem. We'll catch you next time on The Deep Dive.
Until then, keep exploring.